Okay, so we looked at example one last time. So we have a second example here. It says you have a 40-watt incandescent bulb. It's about 1 joule of visible light energy every second. Calculate the number of visible light photons emitted per second. So a 40-watt incandescent light bulb, first of all, incandescent light bulbs are the ones that have like a little filament. We're not talking LEDs, we're not talking fluorescence, we're talking about the old incandescent light bulbs. So first of all, you guys should know that that is the first type of light bulb that was invented over 200 years ago, and they're not very efficient at all. So even though it's a 40-watt bulb, remember watts is joules of energy used per second. So a 40-watt bulb is using 40 watts of energy, 40 joules every second, but only about 1 out of those 40 joules is actually converted into visible light. What's the rest of that energy converted to? Heat. So it's important to note that there's a reason why about 5 years ago or something, the U.S. government made it so you couldn't buy incandescent light bulbs anymore. And I thought it was really weird that people got upset about it. People were like, but the government can't tell me what to do. The light bulb. I just think it's weird that people were like fighting over like 200-year-old technology. Like you can't manufacture cars from like 100 years ago and sell them as new today because they don't meet like emission standards and all these things. It's just like, nobody's upset about that, but for some reason, 200-year-old light bulb, like, give me. So, anyways, so this should make sense. They're horribly inefficient, which is why, like, you can buy like an LED bulb that literally uses like 3 watts and it puts out more light than a 40-watt bulb because they're actually pretty efficient. So, it's only about 1 joule visible light energy. I just want to address the difference between those two numbers there. Then calculate the number of visible light photons emitted per second. So we know the energy, right? So to do this isn't too bad. So the energy, in this case, is 1 joule, right? So we have our equation that E equals HF, right? Now, you can't just jump over here with Planck's constant because is this 1 photon that's going to come out of here? No, it's not. So we know the total energy, but that's the total energy for all of the photons coming out, right? So we have 2 issues here. Number one, this isn't going to work just for 1 photon. I mean, this is an equation for 1 photon, but that's obviously not 1 photon coming out there. And the other issue is we have this unit of joules, and we need to convert that to a more useful unit. So okay. So here, the total energy is going to be the number of photons times the energy per photon, right? That makes sense. Because our total energy is 1 joule, but that's way more than a photon. So what I did here is my total energy is 1 joule. We can see that. And then that still means number of photons times energy per photon. So energy per photon, like where did I get this 3.6 times 10 to the negative 19? Well, I got it from over here. So last class, I said that 550 nanometers is the approximate average wavelength of visible light. Light bulbs put out many frequencies, so many different colors of light will be seen. But together, they all come out to this sort of yellowish, whitish color. And so we're just taking the average photon, well, that would be this guy over here. Does that make sense? So the average photon has 3.6 times 10 to the negative 19 joules per photon. So we know that. This isn't something you got to like memorize. This is just an example. So all we have to do is figure out how many photons, just multiply times this. So obviously some photons will have a higher energy and some will have lower energy, but on average, that's why we're using that. So then we just solve, for n, and so we take 1 divided by 3.6 times 10 to the negative 19th, which comes out to about 2.8 times 10 to the 18th photons. If you look over here on the chart, and the 18th is a quintillion. So almost 3 quintillion photons are emitted per second from your average light bulb. And it should be noted that these are visible light photons. We already talked about the rest of that energy. The other 39 watts are essentially given off as heat, and they would be given off in the lower frequencies that we can't see. So like, probably not too many radio photons, but definitely a whole bunch of infrared photons. And so you get roughly 39 times that amount of photons given off just in infrared. You okay with that? So that's why I put these two problems together, because there's no reason for you to know this. Okay, so I'm going to introduce a new unit, but it sort of is. A lot of times using joules, you might notice, leads to us having very large numbers. And if we're talking about like individual photons or individual electrons, dealing with, 2.8 times 10 to the 18th photons is kind of a lot, right? So a lot of times we use a unit, instead of joules, we use a unit called the electron volt. Electron volts is the amount of energy equal to the work done on an electron and accelerating to a potential difference of 1 volt. So this is one of those things that would make more sense if we had done it after electricity and magnetism. But you guys know that we can have volts, right? Like how many volts come out of the wall? Do y'all know? You never stuck your finger in there and find it?
More than 6, like 7, 9.
So in this country, it's between 110 and 120. So on average, 115 volts out of your standard wall socket. Now, you might notice that different countries have different shaped outlets, and that's not just to confuse you, it's because they have different voltages. You don't want to generally plug in things that have different voltages. So for example, it's like 110, 120 here, it's more like 240 across the little Atlantic Ocean. So, don't want to just plug that in. But anyways, the whole deal is essentially if you do work to push an electron a certain distance, if that work comes out to be like this. So here, we haven't reviewed this year, but y'all should have talked about Coulomb's law last year, right?
No. I don't remember.
Well, I guess because y'all had the thing last year. Because this is what you would go over like right
Is this the circuit stuff?
This is right before.
We need to get that.
Yeah. So, okay, well, theoretically, we're going to go over it this year, but not right now. But this is Coulomb's law. That's the K, Q1, Q2 over D squared. So this is charge 1, charge 2, with the distance between them. But basically, essentially, if you that'll allow you to calculate the force. And so if you have, like, say, 1 electron here in space, let me just draw this. So if you have, let's say, 1 electron here, 1 electron here. So let's say that something is holding this second charge stationary. If you take this guy here and you think about bringing it from an infinite distance away and you push it, you apply a force over a certain distance here, right? You can do work. And so if they're both the same charge, let's say they're both electrons, so they're negative. So when you push it, you have to apply a force over the distance, because 2 negative charges, are they going to attract or repel? Repel. So I'm pushing it, and like this one doesn't want to go this way, right? So I'm going to have to physically push it against that. And I can calculate how much force using Coulomb's law, like how much force is there, and then times the distance it goes over to find the work done. But essentially, because of voltages and whatnot, we can simplify it to Q1 times V. So like this thing will have a voltage. You can think of it like in like concentric circles around this thing. But like, at this point, let's say it's got, 2 volts, this is 3 volts, this is 4 volts. Or sorry, that's backwards. My gosh. So 2 volts, 3 volts, 4 volts. Because you get more voltage as you get closer. So essentially what we're saying here, what an electron volt is if I was taking this electron from here to there, that's a 1 volt difference. Y'all see that? And so if I push it over that, go from this voltage to that voltage, and I have just 1 electron, that's 1 electron volt. It's essentially, how much energy it would take to move this electron from point A to point B. Now that's just one given scenario. There could be billions, but I'm just trying to get y'all to do this, that essentially, because of the way the units work out, that force times distance ends up being the same as Q times V. Now, force is measured in newtons and distance is measured in meters, but this unit comes out to be a joule. This unit comes out to be a joule as well, but, so right here it says 1 electron volt is 1.6 times 10 to the negative 19 joules. And that's because an electron has a charge of 1.6 times 10 to the negative 19, right? So coulombs of charge. So if you don't know that, that's written up here, or written in your book, written on your equation sheet. So essentially this is just, 1 volt times the charge on an electron. So instead of putting the electron's charge into this equation, just think about this as just like, it's the charge on electron times whatever voltage there is. And so essentially we can use electron volts. They're equivalent to joules, if we make this conversion factor here. So the nice thing is if you're talking about like individual electrons, protons, whatever, this is going to be a lot more convenient, right? Instead of this monstrosity here. So a lot of times we're going to use electron volts when we're talking about individual like atoms. And so here, this is taking our average, energy per photon, which we looked at on the last slide here, and we're converting it, instead of it being joules per photon, this should be joules per, or electron volts per photon. And so the average visible light photon comes out with about 2.26 electron volts, which again is basically nothing in terms of joules, but it gives you an idea. Now, the reason why we use electron volts is because, well, let's just go right here. I've already said, it's more convenient, but go. So for example, depending on its energy, a single photon can cause a molecular transformation as it does in the sensory system of your eye, or even break covalent bonds. So for example, if you have a photon that comes in and it has at least 0.24 electron volts, that can break a hydrogen bond between 2 molecules. Now again, the hydrogen bond is pretty weak, right? Energy released in metabolizing 1 molecule of ATP. I know this is not a biology class, but you guys should remember ATP at least. It does something, right? So the energy released is about 0.32 electron volts. And so you can see that like down on the molecular level, like an electron volt is a much more reasonable thing, right? If we were writing this stuff in joules, this would be like 0.65 times 10 to the negative 19, like, these are just easier to manipulate. Then breaking the bond between atoms and a water molecule, so actually breaking like the hydrogen off of like the oxygen, that takes 4.7 electron volts. And then here, a very interesting one is ionizing a hydrogen atom takes 13.6 electron volts. And that's interesting because that gives us kind of a baseline, because how many electrons does a hydrogen atom have? 1, typically. And so the thing is if you have 1 photon that comes in and the photon has 13.6 electron volts, if it hits that electron, that will cause it to not jump up to just any old higher energy level. It will cause it to have enough energy to break free of its atom and just start flying off by itself. And that's the energy of ionization, because that's what an ion is. It's an atom, but it has a positive or negative charge, right? Because it's either lost or gained electrons.
Where's the
What's up?
Where's it go?
The electron?
Yeah.
Well, it'll fly away from that atom. It'll probably get caught up on some other atom in a second. But so this is interesting here because now we can start to see how like just light, just these photons interact with, say you and your skin. This is why like sunlight can cause burns, because it has energy that comes in. And if it can do things like ionize hydrogen atoms or break bonds between atoms, like that can do damage to your cell, right? So atomic spectra, we kind of talked about this already. Atomic spectra are the specific electromagnetic frequencies that are emitted as electrons change their state of energy. So I pointed this out yesterday. I have that periodic table, the spectra down there underneath the other periodic table. So you can see that like each element has its own unique spectra. Obviously the periodic table spectra is only, that one only shows visible light. There's obviously still spectral lines like an infrared and the radio and the gamma, but we can't see them, so what's the point of putting it on the table? That's kind of why like these things down here, that's part of the reason why a lot of these turn black, because they have different energies. But the other problem is we don't necessarily have enough of those to test. Each element has a specific spectrum, hence that. Electrons have specific states of kinetic energy in an atom. As an electron absorbs or emits energy, they can change orbitals. So again, they want to be in their lowest orbital most of the time, but again, if a photon comes along, it can increase that energy and cause it to jump up or down. But this is very specific amounts of energy, which is why they have very specific spectral lines. Think so? Did y'all do that in chemistry where we looked at the spectroscope?
No.
Some?
Maybe
did. Sorry. I mean, we'll do it in here. Not today. Okay. Solar spectrum. So, although our white appearing sun, the sun is white, emits light of nearly every color, it does indeed appear brightest in the yellow-green light. Dark patches in the spectrum arise from gas at or above the sun's surface, absorbing sunlight emitted below. Since different types of gas absorb different colors of light, it is possible to determine what gases compose the sun. Helium, for example, was first discovered in 1870 on a solar spectrum and only later found here on Earth. So helium was first discovered on the sun. Today, the majority of spectral absorption lines have been identified, but not all.
Is that why it's called helium?
Yeah.
That's crazy.
It's named after Helios, the god of the sun.
I just thought of that. That's crazy, really crazy. You the first one that's ever been thought of?
Yeah.
It's crazy. I think that's what two people.
Okay, so here, this picture, this is an actual photograph of the sun's spectrum. If you click on it, it actually takes you to the astronomy picture of the day.
Dude, the sun got some dead pictures.
And so here, you'll notice that what this says right here, I just literally copied word for word for the thing.
That's plagiarism.
So the whole deal here is this is from NASA, and the nice thing is you can click on all of these different things, and it'll take you to the definitions. Like, for example, if you don't know what helium or prism is.
What's the definition of first discovery?
I
don't believe in NASA. You believe in the moon landing?
So here you can see that the sun wants to emit all of these colors, but the gases on the sun absorb some of these, and that's why we get these holes essentially in it. So this is just the visible part of the spectrum, and obviously it's stretched way out. If you were to point a spectroscope at the sun and look at it, you wouldn't see this because your spectrum would probably be too small. Also, don't stare at the sun. Seems like an obvious thing, but So electromagnetic spectrum, I've mentioned it several times. This is more or less the full spectrum, although there technically is no end point. So we have essentially gamma rays on one end, and then we have, so gamma, X-rays, UV, visible, what we can see, then infrared, microwave, and then radio waves. A lot of our stuff here on Earth is built around radio waves and infrared and lower, because they're a lot easier to deal with. And when I say easier to deal with, most of you have probably seen pictures or videos or like movies where you see like the big radio telescope arrays. Like out in New Mexico, we have the very large array. It's I think it's 15 radio telescopes, and they can use them independently, like a regular telescope, or they can use them together. And when you use it, when you use multiple scopes together, what's interesting, and this works for visible light telescopes as well, is with computers, we can essentially take two electromagnetic signals that are coming in, one coming in each one. But if you're looking at, say, like the same star in the sky, what you end up realizing is that they'll get the same light, but it'll arrive at two different times because they're in two different spots, right? It'll be slightly ahead over here. And so you can use a computer to adjust for that and be like, okay, this one's a little bit further, so it's going to take this much longer. And then you can combine the light from both scopes. And what's interesting is when you do something like that, it's called interferometry. When you do something like that, the resolution of your telescope is not the size of your dish anymore, right? So if we're talking about radio telescopes, but this also works for, like I said, visible light and all enough. It's not the size of the dish anymore. It's actually the distance between your two telescopes is the resolution of your scope. And so there's been plans, like proposed plans to, essentially we have radio telescopes because of different countries on Earth pretty much spread out over the surface of the Earth everywhere. But if we put one, say, like in orbit around the Earth, we would essentially get a telescope the size of the Earth.
Crazy.
Or we could say put one on the moon, or probably a couple, the moon turns. If you put, let's say, like 4 to 6 scopes on the moon, well, then you could have a radio telescope the size of the distance between the Earth and the moon. Which I know it seems like the moon's like right there, but if the moon goes all the way out and it's highly elliptical orbit, it's not very elliptical at all. If the moon's all the way out, all of the planets can fit between the Earth and the moon.
That's crazy. That is pretty crazy.
Yeah, like most people don't realize just how far away the moon is. But here's the deal. We do that all the time with radio waves. It's actually super difficult for us to do it with visible light waves because they have such low frequency or such high frequency. And we pretty much do it with nothing above that with multiple scopes. We have a couple of visible scopes. Actually, the Keck Observatory in Hawaii is actually not one, but 2 10-meter telescopes. That's the diameter of the mirror is 10 meters. To put that in perspective, the height of the school is about 10 meters. So there's not one, but there's 2 of those in Hawaii, and they're pretty, they're on this. Typically the scopes are used separately, but they've tried to put them together, and even with today's technology, the computers struggle to keep up with visible light. So it's theoretically possible, it's just in practice, like we can do this stuff down here, like interferometry, but up here, we're still struggling to make it work. Photoelectric effect. So photoelectric effect is one of those things that is probably super important for you guys, but it's a little hard to understand. Basically, when we talk about the photoelectric effect, I'm not going to be sending out a bunch of equations and stuff. The deal with the photoelectric effect is that it's all about the frequency of the light. Because essentially, what happens, and this is one of those things that like Einstein was talking about, is that it turns out you can shine light on a surface. So in this case, let's say it's sodium, some chunk of metal. So we shine light on the surface, and electrons can actually be ejected from the surface. So if you think about something simpler, think about like hydrogen. which we already talked about, if I have photons of the right frequency, of the right energy, when it hits those electrons, the electrons will just leave, right? It'll ionize your substance. But it's all about the right frequency. And so essentially what they did is they had experiments where they would have this piece of metal hooked up to a circuit. And essentially, this piece of metal is hooked up to a circuit that will just feed it more electrons if it needs it. And if this is full of electrons, no more electrons are going to show up. Does that make sense? So you can almost think of it like a battery is being hooked, but just like the negative end hooked over here. And then let's say we hook the positive end of our battery over here that will like attract these electrons once they get ejected. What's interesting here is that if you shine a light on it, you can start to eject some electrons. But it's all about the frequency of the light. Just making the light brighter doesn't really give you more electrons ejected. And that's counterintuitive because most people are like, well, you get more light, it's clearly brighter, you're clearly giving more energy, so I should get more electrons. Well, that doesn't work. What works is tuning it to the right frequency for like that particular substance. Does that make sense? If I emit more light of the right frequency, then I can get more current flowing. So how is this important for your life? Well, right there it talks about solar panels, and that's essentially how solar panels work. Like light comes in from the sun, hits your solar panel, eject some electrons, and then you capture these electrons, make them go through a circuit to do work, and then you make the circuit dump the electrons back in heat. But it's more than that. Pretty much anything that you use a remote for is the photoelectric effect. For example, if you have, let's say, a garage door opener, you push the button on it. Well, when you push the button, it sends out usually an infrared wave in all directions, like in a circle or sphere, I guess you could say, out from, let's say, your car. And when this of the right frequency hits your detector in your garage, it goes, oh, okay, I need to open the garage door. But how does it know that? Well, the electric circuit is going to be hooked up to something like this, and when the electrons are ejected from it, it has to be the right amount of current for the door to open. Because this current will be ejected whenever you hit the infrared button. But if you've ever had, let's say, a neighbor, and they also have a garage door opener, hopefully their garage door doesn't open your garage door, because they're different frequencies, because it's all about the frequency of the light, not just the intensity. Otherwise, just shining a bright flashlight on your garage and make it open. That doesn't work. But like everything, like your TV remote, like that, speaking of your garage door, at the bottom of your garage door, you know, that little invisible line you have to jump over when you do Olympics, right? Call it garage door Olympic trend. The way that works is, again, the same thing. You have this infrared beam shining across from one side to the other, and it's causing a particular current to flow on the other side. As long as that current's flowing, the garage door knows there's nothing blocking, right? So this photoelectric effect affects so many different things that you guys deal with every day in your life. And here's a little simulation about the photoelectric effect. TripJ is a Java extension for the Chrome browser. Otherwise, this thing wouldn't work on your Chrome browser. I mean, it would still work on my computer because it's a Windows computer. So here, I can turn the light on. Let me slide it over here. So here you can see this is essentially a normal circuit, and I can increase the intensity here. And so notice that I get a little bit, you know, if I just crank the intensity all the way up. But if I tune it to the right frequency, you know, so I can get different current. So like here, I'm getting absolutely no current. But if I go to the right frequency, so now it says I'm getting like 1.2 amps of current. But you need to notice that like at this point here, it's like 1.6. But then as I go higher, it decreases. So, like I said, you just got to be careful about all that.
And I believe that's it.